Okay, so this talk will have no original research. It will talk about like things from like mainstream computer science literature, but things that are, I think, very important for understanding agents, and that are in particular also the basis for my research agenda. So it's really going to be a talk about like very quick introduction to statistical learning theory, which emphasizes reinforcement learning theory. And reinforcement learning theory is unfortunately something that doesn't really have a textbook or even a survey paper, which is good. So it's kind of hard to get into it, but it's really important field for our purposes. So we're going to have 4 parts. We'll start talking about binary classification in learning theory, then multi-arm bandits, then decision process, and finally we'll get to reinforcement learning, which is kind of really the goal in some sense. So binary classification, like the reason I talk about it is because that's in some sense the simplest setting in learning theory, and it's kind of like a prototype of all the different other learnings. Like it's easier to study and understand it, but the phenomena that happen there, they kind of reappear in other forms in many other learning settings. So binary classification means like, you have some data and you need to classify it. For example, like there are pictures of cats and pictures of rabbits, and your algorithm needs to learn which is which. So formally we have like X is some space of instances, for example, space of images. Like D is, so we're going to have D as some distribution. So this is supposed to be element and not subset. Element of delta X. So there's some distribution of like how often different images appear in nature. And F is some unknown function from X to 0, 1. Whether it's function that reads the image size, or it's a cat image or a rabbit image. And so what is a learning algorithm? Learning algorithm is a mapping pi from a sequence of images and labels, right? This is our data set. Like we'll begin an element of X and label, element of X and label. And like then a new image comes in and we need to assign a label to the new image based on what we've seen before. So we want to have like some notion of like what a good algorithm means, what a bad algorithm is, and how good can algorithms be, and so on. So for this, we usually relatively judge algorithm relatively to a particular hypothesis class. And so this hypothesis class is some class of how things could be. And there is the realizable setting where we assume that the world is actually described by one of those hypotheses. The agnostic setting where we assume the world can be approximated by one of those hypotheses. Actually, in this talk, I will only talk about the realizable case for simplicity, but there is also theory in the agnostic case. So for example, maybe my data is like points on the plane, and my labels are some points are blue and some are red, and my hypothesis is there I can draw some straight line such that all the reds will be on one side, or the blues on the other side. So this is like a possible hypothesis class. Okay, and then we can talk about risk. What is risk? So risk is like how, what's like the error of my algorithm. So formally, the risk for our purposes is going to be, so it's a function of the algorithm and of n, which is like how much data I've seen. And it's going to be a supremum. So we're looking at the worst case analysis here. So it's a supremum of all possible distributions that can be on the space of instances and all the functions in my hypothesis space, because I'm assuming that some hypothesis is correct, with the probability I will be wrong, right? So the probability if I sample some data set by sampling instances from here and then applying this function, and then I sample some new instance, and I look what my algorithm is telling, like how it's labeling this instance, probably I'm wrong. So this is the risk. Then I want algorithms that have low risk. So what can be said about it? And here is like the classical old good old theory, which is Chervoninski's theory, which explains how, in which cases and how we can bound the risk. And the theory says the following things. So there's a notion of shattering. So, okay, what does it mean for? So a set of instances shatters the hypothesis class when for any way to assign labels to this set, there is some hypothesis which assigns label in this way. So for example, if my hypotheses are like lines, then for any triangle is shadowed, because like, not any triangle, but triangle is not on the straight line. For example, it's shadowed because like no matter how I color the vertices, I can find a line that passes such that the blues will be on one side or else on the other side. The VC dimension, the Vapnik-Chervonenkins dimension of a hypothesis class, is the cardinality of the larger shattered class. And it turns out that this combinatorial property of the class is more or less characterizes how well I can do in terms of risk, basically completely. So the main theorem is like that the best risk I can achieve is like in the realizable case is going to be O tilde of the VC dimension of H divided by N. So the risk, as I learn more and more samples, it reduces at a rate of 1 over N, and the coefficient is, yeah?
I'm curious how this risk perspective, how it compares to a Bayesian perspective.
I mean, they're kind of related, but like in risk we have like, we're looking at like the worst case. So in some sense, I maybe have another word about it later. So in some case, in learning theory, there's like uniform bounds and non-uniform bounds. And like uniform bounds is just the worst case, whereas non-uniform bound is like for different hypotheses, we have different rates. So in some sense, uniform bounds from Bayesian perspective is, you should imagine like having like a uniform prior, or like not caring about your prior. Whereas like when you're doing non-uniform learning, then it's kind of really closer to the Bayesian perspective, where some things have low probability in the prior, so you allow them to have like a worse rate or something. But like in principle, you can also study Bayesian, like statistics and learning theory, like risk, they're also Bayesian analogous, right? We could do like Bayesian risk, which would be if we had like an expected value over the function over the hypothesis space instead of like worst case. Those things are related, but I'm just not gonna talk about it in this presentation, but they're strongly related. And yeah, this is actually the next slide. So the next slide is non-uniform learning. So non-uniform learning is like, okay, instead of doing the worst case over all hypotheses, let's just consider each hypothesis separately, right? So let's define, and by the way, this rate is like, it's both a lower bound and an upper bound. This is like the best you can do. You can do it, but this is also the best you can do. And if the VC dimension is infinite, then it's just not possible to have the risk converging to 0. So it's like a very full characterization. So in non-uniform learning, we say, okay, instead maybe we want to tolerate different rates and convergence for different hypotheses. So we can define a hypothesis-dependent risk that depends on F, which is going to be just soup over distribution, so we're still worst casing over distribution of the same thing, the probability that my algorithm will be wrong. And it turns out in this case, still VC dimension is like a key characteristic to define how this thing behaves. And specifically, we have a theorem that says that like there exists some algorithm such that for all policies, this thing stands to 0. So now it's non-uniform because it's not like the maximum of them turns to 0, but everyone separately turns to 0. If and only if the hypothesis class is a union of a countable set of classes such that each of them has a finite dimension. So now, you know, before, when we talked about uniform learning is possible if and only if the VC dimension of the entire hypothesis class is finite. Here, we weaken the condition, we only require non-uniform, so now it's possible if we can split it into some countable union such that each part has a finite VC dimension. And classical example of that would be like polynomials, for example. Like polynomial regression is a classical example. So we have like two variables, and our hypothesis look like there is some polynomial such that when it's positive, it's like blue label. When it's negative, it's red label. Like these are my hypothesis. So this thing has an infinite VC dimension, but if you look only at polynomials up to a particular degree, then it's going to have some finite VC dimension that depends on the degree. And this is why you can learn, and there's like specific algorithms that give you some optimality, like it's called structural risk minimization, that like tell you what's the degree of your polynomial should be, like what degree you should be trying to fit as a function of how much data you have. Okay. So yeah, so and another thing is that's like, when you think about description complexity, that also often enters. So another like typical example would be that my hypotheses are described in there's some language which describes my hypothesis, and then like if I limit the length of my description I allow, this gives me some finite VC dimension. And that's also kind of related to the Bayesian perspective when you kind of assign lower probabilities to higher things. Yeah.
How does the dimension behave under unions? Is it like additive or separate?
It's so the dimension of a union is between the maximum of dimensions and the sum of dimensions plus 1. Yeah. Okay, and so kind of to summarize this part, so I started by saying that binary classification is kind of the prototype problem of learning theory. And one of the takeaways that are interesting from here is that there's some notion of dimension. And it's kind of intuitive, like, you know, if physicists think about theories, they also think like how many free parameters the theory has. So there's also like some notion of dimension. And it turns out that in many different settings, in learning theory, there's some notion of dimension that controls how good, like how quickly your learning is, or how good your sample complexity is. So like for binary classifications, the VC dimension. For multi-class classifications, the Natarajan dimension. For online learning, it's something called Littlestone dimension. There's some single learning theory, which has like this RLCT thing, which is something also analogous, some notion of dimension. And for reinforcement learning, by the way, this I won't actually talk about it here, but it's kind of been an open problem for a while to understand what the relevant notion of dimension is. There was something called the Luder dimension and Bellman-Luder dimension, but there's some recent paper by Microsoft Research that comes up with something called the decision estimation coefficient, which seems like it's already more or less the right thing. So we have like analogous things. But we'll see some simpler kind of dimension of the resident learning theory later. By the way, feel free to ask questions because, like, yeah.
Can I ask one?
Yeah, sure.
Just on the previous slide, it might be something you get into later.
Sure.
So I think I have a good geometric intuition for, say, the VC dimension in binary classification. How could I imagine that for reinforcement learning, where my picture is something like, oh, I have an agent that kind of goes around that creates like its own next inputs or say observations, you know, like. Is there like some similar geometric picture that I can keep in mind, or is it not a good idea?
I mean, yeah, there is something, but I don't know. I feel like the answer will take me too far aside, but maybe we'll go back to it after.
I do have a question.
Yeah.
Obviously, I'm the big RLCT guy. Big fan of that. Is there a sense in which there is one general dimension and there are all specific cases of this? Of some...
Yeah, good question. So I'm not sure, but like I think that some of those, and for example, like binary classification is a special case of reinforcement learning. Like if you assume that your state transitions are all IID and like you set it up in the right way. So I think that I'm not sure that this is actually true, but it seems like it should be that, for example, if you take this object and take like a hypothesis class which looks like it's just doing binary classification, you'll get the VC dimension. I don't know where, it sounds like it should be true, but I haven't actually. Okay, so now we get like our next learning setting, which brings us kind of closer to reinforcement learning or to agents, which we want to do. And that's like multi-arm bandits. So multi-arm bandits, So multi-arm bandits, the reason they call it like that is because of slot machines in casino, right? These slot machines are sometimes called the one-arm bandits. So here you have like several arms that you can pull. That's why it's called a multi-arm bandit. So actually, Kaspar already talked yesterday about multi-arm bandits, but this was mostly going to focus on adversarial multi-arm bandits. And here I'm going to mostly talk about stochastic multi-arm bandits. So, okay. Right, so what's a stochastic multi-arm bandit? So there's some set of actions, and for each action there's some distribution over rewards that happens if I pull this action. I don't know it, but it's there, and it's fixed. And like an algorithm is given a sequence of actions and rewards, like what's the next action I'm going to choose. So yeah, in adversarial it's actually important to have the algorithm stochastic, but here it's not important, it could be deterministic. Yeah, and then like given such a thing, given this distribution and given the policy pi, we get some distribution over like infinite sequences of actions and rewards, right? I have like my algorithm, I have like the distribution, I choose action, I get something, I choose a new action, I get something, I choose a new action based on what I've already seen, and so on. So, yeah, so, okay, and now the relevant notion, so instead of talking about risk, now the relevant measure of how well our algorithms are doing is something called regret. So what's regret? And so the regret of my policy pi as a function of n is, so we're doing like a maximum over all arms, over all actions of the expected reward I would get. This is like the best reward pair round that I could hope for, right? It's like if I knew what the best arm is, minus like 1 over n of the expectation over this distribution of the sum of rewards. So in other words, I'm looking...
The gap between the theoretical best expected reward and the expected reward you actually have.
Yeah, like the expected reward I would have per round if I knew what the best arm is, whereas what my policy actually does. And so in this talk, I'm going to normalize all the rewards by dividing by n. So a lot of times in the literature, they won't do it, but this way it's more consistent with risk and with other things. And the bounds you get for this are that in the distribution independent case, so if I'm doing just worst case over all distributions, then what I can get is O of square root of number of actions divided by n. So if you remember, in VC theory, we had 1 over n. Here we have square root of 1 over n. It's like a more difficult problem, so the rate is not as good, but it's still good. In the distribution dependent case, so if I'm looking like separately for each distribution what the rate is, instead of doing worst case over all distributions, I get something even better. I get log n over n. Still not quite 1 over n, but it's already much better. But here there's some coefficient which depends on the distribution. And it actually depends on the gap between the best arm and the second best arm. So when they're really close, then this coefficient will be large.
So that's the spectral gap or the mixing time of the...
No, it's not really, no. It's just, it's not eigenvalues or anything. It's just like the best reward and the second best reward. It's just like...
Yeah, I mean, that would be my first association.
If that gap is small, then
it
doesn't really matter which one you pick, so it shouldn't lead to like a large reward gap.
I mean, if they are small, then it's harder to know which of them is better. But now, it's true that it also matters less, and this is why you still have this. So no matter how small the gap is, you're still going to have, like this thing is still going to 0. But the rate at which it's going to 0, if you're just worst casing, it's going to be square root of 1 over n, whereas if you're just like a fixed.
Okay, I see, okay.
Mm-hmm. Okay, and, okay. So this is actually something we have for adversarial bandits too, but this is something we don't have for adversarial bandits. Okay, but so far it was like, okay, so what's bad about this? Bad about this, one thing that's really bad about this is it scales with the number of actions. Like what if I want to have like a ton of different actions, right? And so this is kind of similar to how, imagine if I was doing binary classification and I was, like the set of possible images was really small or the set of possible hypotheses was really small. I mean, then I would have good rate, but it's kind of not interesting. The interesting thing in the binary classification case that I can use some structure in my space of hypotheses, right? Like this VC dimension, the whole idea was that I have a lot of hypotheses, but this hypothesis space is in some sense low dimensional. There's some structure that can exploit. That's why I have good rate. Here there's no structure at all. Like it can be anything. So how can we do structure? So a simple example of exploiting structure in bandits is linear multi-arm bandits. So what's linear multi-arm bandits? Now our set of actions is just going to be some complex subset of RD. It can be infinite, just some combo. And there is some unknown theta star, some unknown vector in RD, such that the expected reward I get when I take an action is equal to the dot product, right? It's equal to A transpose times theta star. But I don't know the theta star, so I choose different. So, I have, for example, the circles, the actions I can choose, and I can choose some action, and I get a reward which depends on this angle. But plus some noise, because this is just the expected value, right? There's some noise. And I'm kind of doing experiments and trying to converge to. So I want to be choosing actions which are parallel to this theta square, like to get the best dot product in this example.
Is this a very natural way?
This is just a simple thing, but this is just like a thing where it's easy to do the math. But in some sense, in some sense, it's kind of half natural because linear things they're like, it's like in classification theory where you have like support vector machines where you just assume, okay, let's assume there's a linear thing. And that's like a very strong assumption. But then you can weaken it by saying, okay, but maybe there's some embedding into higher dimensional space in which it becomes linear. And the same sort of thing you can do here. So it's still like a big assumption. It's maybe not quite a strong assumption. But it's nice. Like if it was instead of linear, it was polynomial. Then you could just embed everything into by just taking all the products into higher dimensional space and treat it as a linear bandit in that higher dimensional space.
So large D is for like arms with extremely complicated structure, and if there's some like simple structure on the arms, then you can embed it into a dimension that isn't that high and learn it pretty fast.
Yeah, but also it's still but still just linear bandits is just for me is just like a toy model. Like there are other notions of dimension like a lunar dimension, which allow some complicated nonlinear structures that are not captured by this.
So some more elaborate version would be maybe relevant for robotics. Maybe could be a model.
If I have
a robotic arm, there's some dimension of like its face space basically.
Yeah, maybe. Yeah, I don't know. So for me, it's just like a toy model to gain some intuition. So and here you can get a regret which is O tilde of D times square root n.
So, I should know this also applies to the other thing, but I'm confused why, like, the diameter of
diameter?
A doesn't appear. It seems like if we scale...
Oh, I kind of...
Some things are suppressed. Is that...
there is some boundness assumption. Like, you need to... I kind of glossed over it, but you need to assume that the distributions are sub-Gaussian. So they're like, need to be sub-Gaussian, and then like with some not too big Gauss. So yeah, of course, if you multiply all the rewards and
okay, so let's just ignore that is stuffed in these
what?
Until the pause, until the break.
Until the break. Okay, cool. Yeah. Like if you, for example, assume that all the rewards are in 0, 1, then it's fine. Then everything is fine. If you don't assume, then you need to be more careful. Yeah.
Should that regret be going to 0? Is that?
Oh yeah, you're right. It's supposed to be 1. Because I was confused between the different conventions. It's supposed to be D divided by square root of n. Good catch. Sorry about that. Okay, and another variant of multi-arm bands we should consider is the pure exploration band variant. So in the previous thing, there was this kind of exploration trade-off, which is the main thing there, where I want to try, I want to focus on the arm that have been doing best so far, because that has the best reward, but also I want to be trying other arms because maybe there's some low probability that they produce some amazing reward, and I just haven't seen that yet. So there's some like trade-off going on. But you can also consider a situation in which there is no trade-off. Sorry. So it's a so-called pure exploration setting. So pure exploration corresponds to, imagine you can do like experiments in some simulation, then you run a bunch of experiments, and then in the end, after you learn a lot of things, you go out in the real world, which you assume that your simulation is describing really well, and do things, right? Like you learn to drive in a simulation, then you actually drive a car. In this case, while you're training in the simulation, you don't care about the rewards. You only care about learning things that you care about. So this is kind of a different thing. So formally, the way we formalize it is we define something called the simple regret. So the simple regret is, again, take the best reward I could possibly have. But now, instead of looking at the sum of rewards, I only look at the reward on the nth round. And also I allow my algorithm to know the number n. So my algorithm knows how much time it has to train. And in the end of this period, it should output like, okay, like you have to training, in the end, okay, decide now what's the right arm. So, and I look at this difference. And here, the distribution independent bound, worst case bound, is still square root of number of actions divided by n. But the distribution dependent bound is now already goes to 0 exponentially quickly. So it's way quicker than before, but it's distribution dependent. So the coefficients are going to depend on,
What does do these distributions depend?
The coefficients again depend on the gaps. It's a gap.
Spectral gap, well.
Yeah, not spectral, but yeah.
The best and the second best.
Mm-hmm.
Okay.
Yeah. Okay. And I mean, for me, this setting is kind of interesting because, like, for example, in metacognitive agents, for people who heard it like yesterday, I'm kind of thinking about an agent that's kind of doing thought experiments. And this process of an agent kind of sitting and doing thought experiments is kind of similar to this pure exploration setting. Okay. Now, let's talk about decision process. So bandits, that was kind of
2.5 minutes. 3 minutes.
until the break.
Yeah.
Okay, cool.
But now maybe would it be good to do the break now?
We can just do the break now.
Maybe you want to advertise what comes after.
Okay, fine. Yeah, so decision process, so bandits are kind of very naive because there's no state, right? On every round, the game is exactly the same game. Doesn't matter what happened in previous rounds. I don't care about what will happen next round. So now we're going to talk about decision process where the environment has some state that changes as a result of my actions. And the learning of this thing is going to be reinforcement learning. But before we even talk about reinforcement learning, I'm going to talk a little about if I even know, like, how do I even describe my environment in this state, what kind of mathematical object describes stateful environments, and and a few words about like finding the optimal policy if you already know what environment you're in, which, like, you know, in the bandit case, it's just, okay, look at which arm has the highest expected value, choose that arm. That's trivial. But in this case, that's already non-trivial. Like, even if I know the environment to choose what's there.
Okay. Let's do the break.
Let's start? Okay.
I'll go me to tell you 15 minutes.
Mm-hmm. Yeah. Okay. So the simplest kind of decision process sometimes is a Markov decision process. So what's a Markov decision process? It means that, so M, a Markov decision process, is a tuple that consists of S, a set of states, A, a set of actions, S0, which is some element of S, and T. So T is the transition kernel, so it's a mapping from S times A to distributions over S times R. So for any state in action, the transition kernel tells you what's the distribution over the next state and the reward you will get. Take this action. So for example, maybe I have like two actions, A and B, and two states, S0 and S1. And if I'm in S0, I take action A, then with probability 80% I get here. probability 20% I stay here. If I take action B, then with 40% I get here, with 60% I stay here, so on. So this kind of thing. So the nice thing about Markov decision processes is that I can now like ask the question of, well, yeah, we'll get to that. So now I have a Markov decision process. I want to get rewards. So I need to have like some algorithm, right? So that's called a policy. So a policy is a mapping from a sequence of action, state, reward to action, right? I suppose that I saw like some sequence, I took some action, got some state, some reward, and so on. In the end, I decide which action to take. So given a Markov decision process and a policy, I get some distribution over infinite sequences of action, state, reward, right? Again, I have this game here with the policy versus the Markov decision process, but now it's not IID anymore. It's not like in the Banach case. That's why like the causal diagram of it has those vertical arrows, where like each thing also depends on the previous state. Yeah.
So are you not considering like distributions over actions?
You could consider also distribution over actions, but I mean, in some sense, you don't need to, because the optimal policy is always deterministic. But in some cases, it might still be convenient, but it's not like.
But, okay.
You know.
But there are cases in which the optimal policy is stochastic, right?
No, in MDP, optimal policy is always deterministic.
Right. When you have to talk to that.
Right. Okay. Sure. Yeah. Okay. Right. Okay.
I don't think you're informing this.
There are some arguments, for example, why you might want to be stochastic if you're not allowed to take any policy, but you're restricted to some space of policies. And then like, but okay, this, whatever. Right, so this distribution is defined by those two equations, right? I take an action from the policy, and then I sample the state of the reward from the transition kernel. So now, given an MDP, we might reasonably want to find the optimal policy, right? So pi star, we want to find some pi star, which will be the argmax over pi, over the expectation over this distribution that we had for infinite sequences of the utility function, where the utility function is typically the time discounted sum of rewards. So it's the sum of rewards I've seen with some coefficients that I assume here to be, for convenience, to sum to 1. And you can use different shapes of time discount. So one nice thing is that there's always a deterministic the optimal policy always exists, it's always deterministic, and moreover, it's always Markov. So what does it mean that it's Markov? It actually only depends on the time and on the current state. I don't need to remember the entire history. Typical reward discount functions that are used are either the finite horizon case, where I just use a constant, like 1 over n, for every t smaller or equal than n, and then 0. So just have n rounds, just sum the rewards over the n rounds. And another typical thing is the geometric time discount, where I have a geometric sequence. So dt is going to be 1 minus gamma times gamma to the t, where gamma is some parameter between 0 and 1. And geometric has this nice property that the optimal policy is also going to be stationary. So in this case, the optimal policy depends only on the state, not on the time, but only on the state. And what's nice about this is that finding those optimal policies, for example, in this case, we can find a policy with an algorithm that runs in polynomial time in number of states and actions, which is, the best we could hope for, given that's how the MDP was described to us as a table, because it's a tabular setting where it's just a table of transition probabilities. So using linear programming, you can actually compute the optimal policy efficiently. Okay. Another more general thing that we could consider is the partially observable Markov decision process, or POMDP. So what's a
So maybe just to go back one. You told me once, and I just want to share it to the crowd, that I found that useful, is even though there is a polynomial time algorithm, this is polynomial in the size of the state, which is, in usual cases, is going to be exponential in the natural parameter. Right?
Yeah, absolutely. But like here, as long as you're given the MDP as just a table of transitions, and polynomial number of states is the best you can hope for. Right. So if you want something better, then you need some succinct like language for describing those MDPs, right? And then you can hope for an algorithm that's going to be polynomial in the description length, but it's going to depend on what language. Maybe in one of the next breakout session, I will give an example of a language that has this property. Yeah.
Can you get a bound on the power in the polynomial? Cubic?
Power? What do you mean power? What's you're asking? What's the when I say polynomial running time? What's the
Is it like
power?
quadratic?
Yeah.
First I don't remember, but second it's also not a really completely well-defined question, because I mean the reason in computer science we like to talk about polynomial time because it doesn't depend on your model of computation. It doesn't depend on whether you have you're using a one-sided one-tape Turing machine or like a two-tape Turing machine or something else, whereas the power is going to depend on the precise.
Can I ask a question?
Yeah.
So if I think of the utility function U, and it's a function of RT, take some class of functions and manipulate RT, is there a natural characterization of that class such that the pi star, the optimal policy, doesn't change? So for example, if I multiply the reward function by a constant, I'm guessing that the optimal won't change.
So you're asking, given a policy, if I want to infer what the rewards were,
what's the uniqueness of the...
Yeah, I mean, that's like a problem that's studied in inverse reinforcement learning. And yeah, so it's not unique. I don't know. I don't have something off the cuff smart to say about it. So there is some space. There's a lot of ambiguity, but I mean, obviously, the policy is like discrete, right? The policy is deterministic policy. So whereas the reward are like a continuous thing. So it's obvious a priori that there's like lots of different changes in the reward you can do, which are not going to change the policy. But yeah, I don't know. Okay, so partially observable Markov decision process is a generalization where we don't see, so the previous MDPs, we kind of assume that we get to see what the state is. So here is like what happens when we don't see what the state is. So formally, we still have some state space S, but now we also have like an observation space O. And now we have some initial distribution over states and some transition kernel which tells us, given a state and an action, what's the distribution over the next state and the observation I'm going to see. So I'm not going to see the state, I'm just going to see this observation. And the reward is usually assumed to be a function of just the observation. For example, maybe I just get to see the reward. It's like part of my observation space. And like, for example, you still have two states, but now in S0, if you take like action A, then there is like 25% probability of seeing observation 0 and staying here, a 25% probability of seeing observation 0 and going here, a 25% probability of seeing 1 and going here, and a 25% probability of seeing 1 and staying here, and so on and so forth. So this kind of seems like a nice thing, right? We want to talk about state spaces that we don't observe. It seems natural, but what the catch is that now computing the policy is p-space hard. So it's like really non-tractable, and even like approximating it is p-space hard. So it's very. So of course, like always, there are heuristics you can use, and sometimes they will work, sometimes they won't work. But in general, in the worst case, it's p-space hard. That's why they're much less popular during theory than you could expect. Another thing, which is like which is a cousin of Markov decision process, which is much less known, but deserves to be way more known, is the regular decision process. So regular decision process is when, you also have a state space, an action space, and an observation space. So it's really a special case of a partially observable Markov decision process. Now we're going to have an observation kernel, which is a mapping from states time action to distributions over observations, only observations, not states. And there's also a transition function, which is a function from states time actions time observations to what the next state is. And this is deterministic. Here there's no probability. And the reward, we're still going to assume it's a function for observation, so we could do more complicated things, but. So for example, again, maybe I have like two states, and I have actions A and B, and observations 0 and 1, and here, like if I take action A, then there's a 20% probability of seeing 1 and 80% of seeing 0, but if I see 0, then I will definitely stay here. If I see 1, I will definitely go here, and so on. So what's important here is it's a special case of a partial observable Markov decision process, but although it is kind of superficially only partially observable, in practice we can always compute in which state we are. Because this function, if I've seen a sequence of actions and observations, I can just apply this function many times, and I will know what the actual state is at every point of time. If I already know in which RDP I live. If I don't know in which RDP I live, I'm not going to know. So of course, every RDP can be reduced to an MDP by constructing this T-flat, like this MDP transition kernel, which is just defined in like the obvious way, just like, like do this, like, sample an observation from this, plug it into this function, and get an action, and then like evaluate your reward function to get the reward. So and for this reason, because of this reduction, finding the optimal policy for an RDP is just like reducible to finding the optimal policy for an MDP. But the learning theory is very different. Okay, so now we finally get to talk about reinforcement learning. So reinforcement learning is now what happens where, like, I have a lot of hypotheses, which could be like MDPs or RDPs or even maybe POMDPs, but I don't know which one is correct, and now I'm trying to, to get rewards as good as I can. So one common type of setting in reinforcement learning is episodic reinforcement learning. So episodic reinforcement learning means that the game is reset. Right? So the typical example is to think of a video game where I played a game, I finished playing, got some score, restart from the beginning, everything starts, there's no like memory from the previous game.
In your, it's like very non-trapped in your terminology, would you say that?
Yeah, I mean, it's one way to deal with traps is let's assume we can reset everything, which is nice if we can. It's less good if we cannot. So of course, in real life, we often cannot reset everything, but it's a simplifying assumption that's convenient. Of course, has been very convenient to, in applications like, you've all seen like reinforcement algorithms for like playing video games like StarCraft. It's kind of very similar to this episodic setting. Or like if you're like training a robot, but you assume that you have like a really good simulation of the environment, then you can treat it as episodic reinforcement learning. You just let it, play in the simulation. So, okay, so formally, in this case, we're going to have this horizon h, which is some time after which we reset everything. So everything, it consists of episodes of length h. And then we're going to have this distribution mh pi, which is the distribution over infinite sequences of actions, states, rewards. And the difference between it and the m pi we had before is that we reset everything after every time h. So it means that the actions are computed from pi, like in the history, like before. Well, the history, yeah, and like the history also includes previous episodes for our purpose. The state and the reward, like when k plus 1 is not 0 modulo h, so on all time steps which are not divisible by h, we just use the transition kernel. But when we reach time steps which is divisible by h, we instead reset everything to the initial state. And often here we can also allow, so this is something you can do or cannot do, but let's assume that you also allow the transition kernel to depend on k modulo h. So this is like once, because everything is episodes of length h, you kind of might as well, in some sense, say, okay, let the transition kernel also depend on which time step inside the episode I am. And here you also have a notion of regret, similar to bandits. So what's the notion of regret? So we can define R star to be the argmax over all policies over the expectation with respect to m star and pi, where m star is like the real environment, of the sum of rewards rk from 1 to h. So this is the sum of rewards over a horizon. This is an expected sum of rewards over a horizon that I get with the policy pi. This is argmax over all policies. So this is the best possible expected sum of rewards over a horizon I could get if I knew what the true MDP is, and I normalize it by dividing it by the length of the horizon. That's r star. It's like the best I can do. Now the regret, as before, is the difference between the best I can do and how I actually do without knowing what the MDP is. So meaning that here, I take the expected value over this m star h pi, right, this distribution, where I play many episodes and reset every time, of the rewards I accumulated across n episodes. So now we have n is the number of episodes.
60 minutes.
Remaining.
No, gone.
Gone, okay.
40.
Fine. So 1 over, and I normalize it by the number of time steps, which is number of episodes times the length of the episodes, right? So that's very similar to what we had in bandits. And also the optimal thing is known here we know the optimal rate up to logarithmic factors. There's still some logarithmic gap, which is unsolved, but yeah.
Are we assuming there's no hidden state here?
Yeah, we're assuming there's no hidden state. Absolutely. So, and the regret bound is O tilde of square root of number of states times number of actions divided by n. So you see it's like very similar to bandwidths, only you have the number of states appearing here also, which is not surprising because like for any state you need to learn things. For every
Yeah, sorry. So this is not a MDP or sorry, what is this exactly?
This is MDP.
This is an MDP.
Yeah. This is episodic MDP, yeah.
But and is it now better? Is it because it's episodic? It's bound is better or
Better than what?
than the general MDP case? Sorry, I'm
If it wasn't episodic, you wouldn't be able to get any regret bound at all. Because like here, you're not assuming anything about the MDP. So because of the trap problem, so we'll get to the non-episodic case in the next slide. So the next slide is actually what there's not really a standard name, but here I call it lifelong reinforcement learning, which is sometimes used with slightly different connotations, but whatever, which is like the setting where we don't do the resets, but we just keep playing the MDP forever. So in the lifelong reinforcement learning, we have the problem of traps. For some MDPs, like if my MDP has some irreversible transition that can happen, then it will not be possible to learn. Because if I don't know, there's some door that I can open, maybe there's $1 million there, maybe there's a bomb there that will blow up and kill me. I cannot learn this fact. I can just decide either I take the risk or not, but I cannot guarantee that in every possible scenario, I will do the best thing. Either I will have to miss out on the $1 million in the $1 million scenario, or I will have to explode in the bomb scenario. I cannot win both. So so this is why we need to impose a condition MDP that says that it's communicating. So communicating means that for every pair of states, there's some policy that will lead us from one state to another, given enough time. So for example, this blue MDP here is communicating because I can keep going between states and go from any state to any state. But if I added this red part here, then it will stop being communicating. Once I do this transition, I'm stuck here and can never go back here. So communicating MDPs have a parameter that characterizes them, which is called the diameter. So the diameter of MDP is the maximum over pairs of states x and y of the medium over all policy of the expectation with respect to the dynamics of the MDP with this policy and with the initial state set to be x of the first time step on which the state is going to equal to y. So in other words, I'm looking at how much time it will take me to reach state y, assuming I start from state x, and I'm minimizing over policy, so I'm doing the policy that's going to do it the quickest in expectation, but I'm using the worst case over the pair of states. So this is the diameter of the MDP.
So it's if you're being as efficient as possible in getting between states,
Yeah.
what is the longest it takes to get from a state to another state?
Yeah. Yeah. And now you define your reward. Well, regret defined is kind of similar like before. So R star. So okay, there is like a slight nuance here, but let's see. So R star of n is 1 over n of arg max over policy pi of the expected value of m star pi of the sum of regrets from 1 to n. So here I'm using a time discount, which is like a step function time discount. We could also use geometric, it gets very similar regret rates, but this is more common in the literature to see this finite horizon thing. So here we're looking at the sum of rewards over a time horizon of length n, expectation over the dynamics with the policy, and like we look at the best case policy, and we normalize it by the length of the time horizon. So the best like reward per time we could get, that's R star n. And it kind of depends on this n because maybe it depends. Now the regret of n is going to be like before, the difference between the best I could get and what I actually get, which is again, the same expression as here, only I don't arg max over policies, I just take the policy I actually have. So the expectation with respect to the policy I actually have of the sum of rewards. So you could also, instead of this R star of n, you could also put here a number that doesn't depend on n, namely the limit as m goes to infinity of R star m. Yeah.
Sorry, I have a really much more basic question I think I'm confused about.
Yeah.
Which is, this is more, we saw these MVPs and POMVPs earlier.
Yeah.
And this is more general. But I'm a little confused in what way is it more general?
So previously we talked about you have an MDP, you want to find the optimum policy. Yeah. Okay, there is a linear programming algorithm, you run it, you get the optimum policy. End of story. Yeah. Here, you have some actions you take, and you see transitions between states, but you don't know the MDP. Like you see which rewards you get, you see how you move from state to state, and you see which rewards you get, but you don't know what the MDP is. You need to learn
so
that.
you don't, but do you directly see what state you move to, or you get observations?
No, you just see the state you move to.
But what does it mean to see which state you go to when you don't know?
Your observation space is identical to your state space.
Yeah.
Okay.
And now now it's meaningful to talk about regret, which is the difference between what you get and what you would get if you knew. So this R star here, that's the control theory from the previous section, right? This R star here is what reward I would get if I just computed the optimal policy for the true MDP. Someone told me, gave me the table of probabilities of transitions, and I could just compute the optimal policy, and this is the reward I would have. But I don't have, nobody gave me this table, so instead I get some other reward, which is smaller, and I'm worst casing, those definitions, I'm kind of worst casing over, so I'm implicitly worst casing here over what the real MDP is. So I get this difference, which is the regret. So instead of doing this R star n, I could also take the limit as m goes to infinity of R star m, and just look at the asymptotic reward in the long-term horizon limit. That would still give me the same type of bounds because this limit actually exists. This is a result of MDP theory. But the difference between those two guys is O of 1 over n. So it's going to be negligible with respect to the over square root of n bounds that we're going to have. That's why those two things are going to have the same bounds. Yeah.
I'm also wondering, you started out with showing all these dimensions with the binary classification, etc. How do they show up in these regret bounds?
Yeah, we'll get to there hopefully if I manage to make that far. So here the regret bound that we know is the best So the best upper bound, the best algorithm we know is like O tilde of d, which is the diameter, times square root of number of states, number of actions divided by n. So it's like before, like in the episodic center, but now we also have this diameter. The lower bound is the same, but with the diameter inside the square root, so there's some still gap between the best known algorithm and the best known hardness result, but yeah.
I don't see how we can get any bound if there's always a trap that can...
There's no trap, it's communicating with known diameter. If there is a trap, then diameter is infinite.
We assume that there's no trap.
Okay, I see.
So this is.
Okay, so now we're getting to the dimensions. So far, this is kind of what's called the tabular MDP setting. Like we're just trying to learn the MDP, but there's no structure, right? There's just a set of states, and everyone can have in transition kernel what we want. What we want to have instead is something like we had before. Like there's some space of hypothesis, right? Like in the real world, we kind of want to use some kind of Occam's razor, simplicity prior, or something like looking for some structure, right? So there's some space of hypothesis. We want to assume that not just some transition kernel, but it's like a simple transition kernel in some sense. And this brings us to the functional approximation setting. And there are two versions of this in reinforcement learning, the model-based version and the model-free version. So in the model-based version, the hypothesis class is just going to be some set of transition kernels. Mappings, it could also be reward functions. So mappings from S times A to delta A times R. Well, the reward is here actually. This is so the model basis, we have a class of hypotheses like this, and now we need to learn. The model-free case is, instead of looking at the kernels, we look at the V function or the Q function. So the V function is like the state value function, and the Q function is the state action value function, which is defined as, so V is a function of like S and the time discount gamma, which is like maximum overall policies of the expectation over the dynamics of the MDP, where the initial state is S of the time discounted sum of rewards. The Q function is the same, but we also force the first action to be A. And so in the model-free case, the idea is, let's define our hypothesis not in terms of what the transition kernel is, but in terms of the V function is or what the Q function is. It's like a different approach.
So this is, in effect, simplifying the problem, or what is
It's
it?
not.
It looks more like it's giving you more information. It looks like for model-free, for those two things, you're just getting the reward, but for model-based, you can like peek at the state that tells you.
Yeah. I mean, in some sense, those things are like. I mean, if you ignore this R here, then this is kind of closer to the reward independent perspective. Like, there's something here where there's plenty of results in the literature, both here and here. But I think that's something that's kind of not really, you won't really see in the literature, but you should think about in this context, is that in the real world, you kind of expect the dynamics to be controlled by some simple laws of nature, but the reward function can be really complicated. And I feel that because of this gap in complexity, model-based approaches should actually be more useful in some sense. I suspect, in kind of more realistic scenarios compared to model-free. But if you're ignoring it, on paper, the model-free are doing at least as good, or I don't know.
So, sorry, what do you mean? So you mean in games, model-free does better, but that's an artifact?
No, I mean, there's which theoretical results we know, and there's which practical things we have. And this is like different, so... yeah, I don't know. Let's maybe.
What's lambda at the bottom? Time lambda?
The empty string. So just like the policy when I see just.
Vanessa, you have -1 minute.
Okay.
Minus 0 minutes.
0 minutes.
Okay, then I guess I will just stop here. Yeah.
Okay. Let's thank the speaker. Okay, any questions? Yeah.
I'd like to ask your help, like with some example I have in mind. In the lifelong reinforcement learning case, if I understood it correctly, like the diameter part was supposed to give us infinite for all of the parts of the graph that are basically inaccessible. Or actually, we can access, but we cannot return.
So if your MDP is not communicating,
Yeah.
then the diameter is infinite. Then there's no bound. There's no guarantee. Nothing.
I thought that part of, say, one of the cases that I probably would like to consider for, say, lifelong, for the lifelong case, would be something like, I don't know, the classical movie scene, as you say, like, you know, you open a door, but then you can't go back. And usually in movies, it's like the door where you cannot go back is usually the right one, right? Like, you know, it seems like, you know, I really need to take this step where I can't go back, and that's how I really get out of this maze or something. So if the diameter is infinite, I mean, are we not saying that, well, basically we will never go to a place, a state that might actually turn out to be the one with the highest reward?
So, okay, I'm not sure I understand. So if the diameter is infinite, then there's nothing, if there's some class of hypothesis in general, and like, you don't have any like assumption like the diameter is finite or something, then you cannot guarantee learning, like you cannot guarantee converging to the best reward for the true hypothesis. So then the question is what to do then. I mean, that's like a different question. But like, for example, in the talk yesterday in metacognitive agents, I suggested a way of dealing with it by kind of using kind of thought experimentations or the kind of simulations to find the best possible approximation to the Bayes optimal policy in this case using like information learning. But it's like, yeah.
Okay, I think I'm going to ask to let's thank the speaker again.